Gonna make a couple of videos on work energy power for Unit 3. Um, we've talked about work energy and we haven't gotten quite to power just yet, but we will pretty soon. So I just want to take a moment to try to talk a little bit about some of these things. And one of those things that we didn't really get a chance to talk about in class was this idea of vectors. So to start off with this series of videos, we're going to talk about part 0, vectors. So learning targets, number 0, I can do some things with vectors. I'm not looking for like too much here, but I just want to point out something called the vector dot product and how we do that operation, what it means, and how useful it can be at times. So the first thing I want to talk about is we have vectors, and we know that we can represent some vector. Maybe we'll call it vector A, and we have a bar over the top to represent a vector. Sometimes people will do an arrow, sometimes they will do a half arrow, so it'll look like this. But overall, it's just extra work to do to show the same thing. So I just don't put an arrow in it, I just put a bar. So a vector A has a direction and a magnitude, and we can write our vector A in two different ways. I can think of it as a Cartesian coordinate system. I can think of it as A sub x, comma, A sub y. So it says go some distance in the x direction and then go some distance in the y direction. Or I can write it out using Cartesian, non-Cartesian coordinates, or in polar coordinates, as we'd say. And the difference is that, let's say that I have a coordinate system with my x horizontal axis and my y vertical axis, and I have some vector pointed into it. What this is doing is it's telling us that if we go out in the direction an amount a sub x, and then we go up in the y direction a sub y, we can represent this vector, and we can represent any vector that way. But another way that we can represent this vector is using polar coordinates. So you might have seen those before, or you were first introduced to them when you took trig, pre-calc, or trig algebra 2, or whatever they call it. But this idea is that instead of going out distance x and then going up or down a distance y, we instead go just out a distance r, or in this case it'd be a distance a, and then we rotate by some angle theta. And so what I get is this vector A, and it's the same vector as A in the other coordinate system, but we're just describing it using theta and then this magnitude of or the length of this vector. And so when I say magnitude of a vector, the full vector, which has direction and magnitude, is this notation right here. But if I'm just talking about the magnitude of the vector, I will write just A with nothing else, no bars. Sometimes I'll write it like this as the magnitude. Those mean the same thing. So A vector magnitude is equal to just A, right? Now, the other thing I want to talk about is this direction component. So we can find the theta, and we can convert between these two notations by saying that A vector, the magnitude of A vector, which I'll write this way for now, or just A, that's equal to the square root of AX squared plus AY squared. And we've seen that before, that's our Pythagorean theorem. But to get the angle for this, because this is just a number, this just represents the magnitude, it doesn't give us a direction. So it's basically saying going out in the radial direction by square root of ax squared plus ay squared, but it doesn't tell us how far to rotate. So to find that angle, we have to say theta sub a, just for the theta for that angle, with respect to the x-axis, can be given to us by the inverse tangent, tan -1, of the opposite over the adjacent legs, right? Tangent is sine over cosine, which is opposite over adjacent. And so if we take the inverse tangent, that gives us our angle. So this is how we would convert from these two equations here, allow us to convert from our Cartesian coordinate system and go into a polar coordinate system. So again, a polar coordinate system is when we have like r comma theta, and a Cartesian coordinate system is where we have a point given as x comma y. And both of these are useful for different applications, but for today, we're just going to focus on this Cartesian representation here. So I know that if I want to add two vectors together, and we've probably seen this before, but just to be clear, if I have a vector A and I want to add it to a vector B, I would take my A vector, which is AX comma AY, and I would add it to my B vector, which is BX comma BY. And I use the angled brackets to notate that this is a vector. Some people use square brackets, but we do not ever use parentheses, because parentheses is a point. So the point ax comma ay is right here, but the vector is different, right? It's the distance between the origin here at 0, 0 and this a vector ax comma ay, or sorry, a point ax comma ay. When we do vector addition, you know that we add our x components together, which I'll circle in blue, and we add our y components together. I will circle those in red. And so the result that I would get for my vector would be the vector ax plus bx comma ax, or sorry, ay plus by. Another way that we can notate vectors, for vector a, we could say that it is ax in the x hat direction. You might have seen x hat as I hat, or I direction, and then plus ay in the y hat direction. And so y hat and x hat are these special unit vectors. They have a magnitude of 1, and the y hat points directly up in the y-axis direction, and the x hat points to the right in the positive y direction, or the positive x direction. So they represent our coordinate system, and this is saying that ax is entirely in the x direction, ay is entirely in the y direction. So if I use this notation to do a vector plus b vector, then I would say that is ax, a sub x in the x hat direction plus a sub y in the y hat direction, and that's my a vector. But I'm going to add to that a b vector, which is bx in the x hat direction plus by in the y hat direction. Again, this little up caret, or little hat, 2/3 of a triangle, is called a hat. When we put it over a vector like y vector, it becomes the unit vector. So if I were to do this in polar coordinate systems, I would have an r hat and a theta hat. But that's not something you're going to encounter anytime soon, so we'll just leave it at that. To do this addition, I would add all this stuff with an x hat together, so I'd get ax plus bx in the x hat direction. And in the y direction, I would add those things together, so I would get ay plus by in the y hat direction. And some of these are pointed in the negative direction, some of them could be pointed in the positive direction, and we take care of that by using like a negative or a positive. So it would be like ay minus by, or what have you. Again, there's no such thing as vector subtraction, but we can negate a vector. So if I have the vector b, which is bx in the x hat plus by in the y hat, and I wanted to find out what the vector negative b vector was, well, I just multiply it by -1. And so I get -1 times bx in the x hat plus by in the y hat direction, which is equal to -bx x hat minus, not plus, but minus by in the y hat direction. And I can further do some more stuff to this, and this is not something you need to really worry about so much, but this is really just illustrative. So I'd have bx in the negative x hat direction, so I just move that negative sign in with my hat, because this bx is a scalar quantity, and so it doesn't have a negative sign to it. It's always going to be positive. Anyways, I would add to that a by, which is in the negative y hat direction. So I've just taken those negatives and I put them with my vector direction stuff. So now I have negative b, and if I want to do vector subtraction, it's the same thing as a vector plus negative b vector, which I would then call ax in the x hat plus ay in the y hat minus, or maybe let's keep it with the old notation, plus bx in the negative x hat plus by in the negative y hat. If I put the x stuff together, I would get ax minus bx in the x hat direction plus ay minus by in the y hat direction. So that's how we do vector addition, vector subtraction. You probably all seen this before, but I just want to go back over it because we do need some of this information for later. Okay, so we've talked about the addition, and we've talked about subtraction, and we've talked about, maybe the various graphical methods. If you remember the tip to tail method, where I take vector A, and then to that I add vector B, which would go this way. So I start off at origin, I go from origin to the end of vector A, and then at the tip of vector A, I put the tail of vector B, hence the name tip to tail. And then from there, I just draw my resultant vector, which I'll call just R vector. These are all vectors. I would draw my R vector from the origin to the tip of B vector. So that's like another method that we could use to do addition. If we wanted to do subtraction, we would do A vector plus negative B vector, but B vector points in this direction, and so negative B vector would point in the opposite direction, which would be this way. So I'd have A vector, I would have B vector, and then my result, here's my origin, and my resultant goes from origin to the tip of B vector, and that's my resultant. So we can do graphical methods for addition and subtraction, but there's something that we can't really do well, and that's a graphical method for multiplication. And maybe we could do scalar multiplication. That would be something kind of intuitive, I guess, but for like multiplying two vectors together, something different has to happen. All right, so if I have a vector and I want to scale it by some factor, say b, I would say b times a vector. So b is a scalar. It has no direction, just magnitude. A is a vector. And notice how I have b in lowercase and a in uppercase, because my uppercase with a line over it will be my vectors, and my lowercase without a line, those will be scalar quantities. So b vector multiply, or sorry, b scalar multiplied to a vector, we call this scalar multiplication because it scales a vector. And it makes it larger or smaller, but it does not change the direction of that vector. It can flip the vector around 180 degrees if I were to multiply it by a negative b, or by -1 even. It would just turn the vector to face the opposite way, but it wouldn't actually change it from, like, say, a 90-degree angle to a 100-degree angle. We can't do that with scalar multiplication. So when I do scalar multiplication, it's going to be b vector times a vector, but we have other ways of writing a vector, like say ax in the x hat direction plus ay in the y hat direction. We also have b vector, or b scalar times ax comma ay, and we FOIL this, or we distribute this b to both terms, b times ax, b times ay, and it's the same thing for this notation as well, for the angled bracket notation. So these two things mean the same thing. This is just one way of representing a vector, and the angled bracket notation is just another way of represent the same vector. They mean the same thing, but sometimes one is more useful than the other. Usually for notation with the angled bracket, we do this for something like answers to our vectors, because they're easier to write this way. But when we actually go and do more complicated math, we use this notation more because it's just easier and more intuitive to work with. So when I do this multiplication, I would get b times a vector is equal to ax times b in the x hat plus ay times b in the y hat. Or, using the angled bracket notations, it would be ax times b, comma, ay times b. And notice how the b gets distributed to both directions, because when we scale it, it scales both directions simultaneously. And so we can't just scale one direction or the other direction. If we wanted to do that, we'd have to pick it apart and look at just the x component of the vector and multiply that by b, while leaving the y component out, or calling it 0. So we could do something that would be like b times just ax vector, but the notation for that would be ax times b in the x hat plus 0 times b in the y hat, which is equal to, in bracket notation, ax times b, comma, 0. So I can do that, and that will scale just the x component, but it makes a different vector than b times a vector, right? So just be aware of that. All right. This is one type of multiplication that we can do. And in general, we have two things that we can work with. We have scalars and we have vectors. There's also what we call a matrix. That's something completely different, and it plays by some of the same rules, but also it's all could be different. So we're not going to worry about matrices just yet, or probably at all this semester, unless you take my semester 2 class, which is going to be a math modeling class. So scalars and vectors. If I have a scalar, I can do a multiplication that is a scalar times a vector. I can do a scalar times another scalar, which you do that all the time. That would be like 5 times 10 is 50. I can also do a vector times a vector, and my result could be a vector. But there's another type of multiplication where I would do a vector times a vector, and I would actually get out a scalar quantity. And notice how I wrote this as an x for my multiplication, and this, the second one, so I'll call this 1, 2. I wrote number 1, vector times vector, as an x, and we call this, something different than the other. This, when we multiply two vectors together to get out a vector, we have to do something called a cross product. Cross like x, right? So cross product gives us a vector out when we multiply two vectors. Well, if we want a scalar out, we take a vector dotted into a vector, and we call this thing a dot product. And I already talked about a dot product in class, which, when we talked about work, said work is equal to f dotted in dr, and we integrate that. So what you end up doing is you dot these two vectors, the force vector dot into the displacement vector, and then we integrate. And so you're basically taking two vectors, making a scalar, and then integrating that scalar. So how does this dot product thing work? And again, we're not even gonna bother with this cross product stuff. It's really super important for other things, but for us, we're not gonna worry about it. And I'll talk about the dot product, how to do it, and then we'll talk about special dot product situations that come up. So this is what we're gonna focus on right now, this dot product. And that's the main reason why I made this video today. So if I have a vector A, and I represent it as ax comma ay, and I also have another vector b, which I will represent as bx comma by, then when I do a dot product between a and b, so a dot b, this will be equal to, well, I would multiply the x components together, so I would get ax times bx, and to that I would add ay times by. And there's no direction anymore, because there are these special cases. And some of those special cases are, if I take a hat, x hat, and I dot it into y hat, it is 0. If I take y hat dotted into x hat, that is also 0. If I have any vector that is not, or any unit vector, and I dot it to another unit vector, it'll always be 0. Because when I think about my x hat and my y hat, my x hat I can represent as being x comma 0. My y hat is 0 comma y. And so when I multiply the x components together, I get 0 times x comma 0 times y, which is just the vector 0, 0. And that is going to be 0, right? So anytime I have a dot product between two unit vectors, things with the hats on them, I will get 0, unless I dot x hat into x hat, or y hat into y hat, or if we're working in 3 dimensions, we could do z hat dotted into z hat. This will give me a scalar, because it's a dot product, it will be equal to 1. Why does it give me that scalar value? Well, I get x hat vector, that's equal to 1. I told you it has a magnitude of 1, and it points entirely in the x-axis. So I have 1 comma 0, and I'm going to dot that into itself, 1 comma 0. But this says take 1 times 1 plus 0 times 0, which is just equal to 1. And so whenever I do a dot product between two unit vectors, it's always going to be either 0 or 1. If they're different vectors, or they're different directions, then it's 0. If they're the same direction, it's 1. So back to our this thing here. A dotted into B vector. So I'll rewrite this stuff on the next page, but I need some more room. I have A vector dotted into B vector, which is equal to AX in the X hat plus AY in the Y hat vector dotted into BX in the X hat plus BY in the Y hat. So this says multiply my X stuff together, which means I would get AX times BX, and these are scalars, so this is just a regular multiplication that we're familiar with doing. But then what I have is X hat dotted into X hat, which is 1. And again, no direction. So my direction stuff, when it dots into itself, it either becomes 0 or 1. Then I look at my Y component stuff, which would be AY times BY. Again, just another scalar multiplication that we're used to doing. So maybe 5 times 10 is 50, or 6 times 4 is 24, something like that. But then I have Y hat dotted into Y hat, which is also equal to 1. And so our directional stuff goes away when we do a dot product because of this unit vectors being dotted together, and it just becomes either 1 or 0. So my result is then AX times BX plus AY times BY. All right, so that's pretty much it for doing a dot product. I'll do a couple just to illustrate the point. Let's say I have the vector A, which is 1, 2, and I have the vector B, which is 2, 1. When I do this dot product, if I rewrite these, maybe I could think of it as 1 times X hat plus 2 times Y hat is my A vector. B vector would be 2 times X hat plus 1 times Y hat. So we just call that Y hat. Anytime that you have 1, you can always just write your vector, your unit vector. So just 1 times Y hat is just Y hat. Then to do a dot product, A vector dotted into B vector, I would have to multiply my X stuff together, which would be 1 times 2 times X hat dotted into X hat plus 2 times 1 times Y hat dotted into Y hat. So we know those Y hat and X hat dot products will just be 1. What I get then is 2 times 1 is 2, plus 2 times 1 is 2. I add those together, and my result is 4. So the resultant of a dot product is a scalar quantity, which here was just 4. But maybe let's do it a little bit more concrete example. Let's say I had a force vector F, and this force was 100 newtons horizontally, so 100 newtons in the x direction and nothing in the y direction. And my displacement vector, or my distance vector, d, let's say that that was 3 meters in the x direction and 0 meters in the y direction. So I do my dot product, F vector dotted into D vector, and what I get out is 100 newtons times 3 meters times x hat dotted into x hat plus 0 times y hat dotted into y hat. This whole thing is going to be 0. You can see that pretty clearly. And then I get 3 times 100 is 300. I have newtons times meters, which is a joule. And then my x hat dotted into x hat, well, that just becomes a 1. And so my answer of F dotted into D vector, F vector to D vector, is 300 joules. Let's try another one. Let's say I have an F vector, which is 450 newtons in the x direction and 200, that's not quite 200, 200 newtons in the y direction. And I have a displacement vector, d, that is entirely vertical. And so it is 0 in the x direction and 5 meters in the y direction. So go ahead and try to figure out how much work this is, because this is force times distance. Figure out how much work it is. I'll give you a few moments to pause the video and give it a shot. Okay, so you should have a chance to work on that. To do this dot product, F vector dotted into D vector, I would take my x component, 450 newtons, times my x component of my displacement vector, which is 0 meters. That's times x hat dotted into x hat, plus 200 newtons times 5 meters times y hat dotted into y hat. So y hat is 1, x has 1, but this whole term is going to be times 0, and so that whole thing goes to 0. Then I would have 0 from my x stuff, and for my y stuff, I would have 5 times 200, which is 1,000. And then I have a Newton times a meter, which is a joule. So 0 joules plus 1,000 joules, and that's equal to just 1,000 joules. So a couple things happened here that you might not be aware of, but I just want to point out. When I said in class the only part of a force that does work is the part that is parallel to the displacement. This is why. If our dot product works out this way, it causes, one of these things to go to 0, and so you see that the x component doesn't do any work whatsoever because there's no displacement in the x direction. If we had another force vector, let's say F vector is equal to 100 newtons, comma 100 newtons, and the displacement vector was, let's say, 3 meters, comma 5 meters. So this is moving in 2 dimensions, both x and y direction. And I did this dot product, I would get, well, you know what? I'll tell you what. Go ahead and try to do this dot product and tell me what your answer is. Give you a few seconds to pause. Okay, so F vector dotted into D vector is going to be the x component, so 100 newtons times 3 meters times x hat dotted into x hat, plus 100 newtons times 5 meters times y hat dotted into y hat. So y hat is 1, x hat dot x hat is 1 as well. I get 100 times 3, which is 300 newtons times meters, or 300 joules, plus 5 times 100, which is 500 joules. Overall, this situation would do 800 joules of work. So that's all I really want to talk about for this first video for vectors. The important thing to take away from this is this dot product thing, because it is a really, really important idea. And even though we won't use it too much in this class, once you get into multivariable calculus, you'll need to be able to do this dot product. So I will have another video coming out pretty soon, and it will be on work, and we'll talk a little bit about work, some other videos on energy, and we will go from there. So until next time, have a good one.